all the security aspects of IoT, in which I explained some of the different aspects from devices all the way up to software and solutions that we have come up with for security in terms of IoT. There's also going to be a part about orchestration for Edge IoT, and then we will have a third section specifically on decentralization in the Edge, where these two things kind of come together, and we have very cutting-edge research to push everything to the Edge. So first up, Edge IoT security. The first difference with, for example, cloud computing that we have there is that devices are very vulnerable in the Edge, especially tiny IoT devices. They're located in people's homes or somewhere on factory floors. They're highly accessible. They're liable to physical damage. This can be intentional or unintentional. They're also much more likely to be, well, compromised, for example, in terms of software failures, intrusions, all kinds of issues that can pop up that you don't actually have in the cloud. Some things you can do about this, of course, is you can have failovers. You can assume that the device can fail at any time, so you have a backup nearby, or you have a batch of backups nearby. You can have some sort of attestation or real-time evaluation of your device to see if everything is still functioning as required, to see if all your functionality is still available, or if, for example, specific hardware is damaged or giving you uncertain output. You can also simply exclude suspected or damaged devices from your network, and then again have your other devices take it over from there. This is especially useful for, for example, sensors, which are usually all over the place in networks of certain types of sensors. You can also do it with processing devices. You can simply have 3, 5, or whatever more processing devices. So whenever one goes down, there's plenty of backups to take over the work. The next aspect is runtime security. So once you have some sort of strategy to secure your hardware, your devices, you still have to secure the actual software on them. So the way you run your software will have an impact on the security of your software. For example, do you just run it as a host, a host process, which is very easily compromised? Do you run it as a container, a micro VM? This is all very different in terms of security. Aspects that can influence this as well, simply bad programming. There are always bugs in programs that can compromise security. You can have active intrusion into software processes from the outside as well as the inside. For example, if there's some sort of input device or a keyboard on your device. You can also have corrupt data streams, active attacks using injected packets that can corrupt your data sources. So that's important to isolate your software whenever that happens. The alternatives we have for that, at the moment at least, are containers, which are basically only halfway there in terms of security. So the process is isolated. You have resources assigned to a specific process. It has a separate root directory in the file system. Some of the network aspects are protected, but it's still possible to intrude into the process if, for example, you get into the host kernel. They all share the same kernel, so once you get into the host kernel, everything is compromised. Micro virtual machines are a bit more advanced. They're basically entire virtual machines, but very, very minified. They can only like something on the order of 10 or 20 megabytes for the system image, and then your entire software process is isolated. But there are drawbacks to that we will see a bit later. There are also virtual system interfaces, which basically take everything that's good about virtual machines and try to run it on the local machine. So basically, instead of interacting with the kernel, the host kernel itself, you build a sort of virtualized kernel around your software process, which it can interact with. So at the very least, you protect your host kernel from whatever is running on it. There's also combinations, for example, kata containers, which combine a container with a micro virtual machine. And last but not least, there are some options for hardware security enclaves, which actually create a sort of separate environment within the hardware itself for secure execution of software. So these first options are all software based. This one is actually in the hardware itself, where the processes get isolated. There is a bit of an impact on system resources. So each of these options affects memory and CPU differently, as we will see in a couple of slides. And one more important question is, does the hardware actually support the required security features that we need? Also, does each of these alternatives actually support these features into whatever clients they run? So if we have a look at all these different alternatives here, in terms of resource isolation, well, this is kind of related to runtime security, of course. The better you can isolate your resources, the more secure you are kind of by default, but it's kind of a mixed bag. For example, well, it's actually hard resource control. Containers also have a hard resource limit control, but they don't actually control resource access. Containers, yeah, like I say, they play a bit fast and loose, so you can say this process could use a maximum of half a gigabyte of RAM, but there's no guarantee that any other process won't intrude on the memory somehow if they get into the kernel. What about, for example, discrete and dedicated resources? For example, hardware accelerators, GPUs. You can mount those into containers, but it's actually a lot more difficult to get them into micro VMs because oftentimes you don't have the required drivers for it, or they don't support them at all, or they don't have the right system calls to support such hardware. It's difficult, and it really depends on the alternative. And then there's all the other resources, for example, networking or network namespaces, actual network connections, what types of connections are supported, what kind of network connectivity is supported. Storage access is also very well variable in terms of support. Local access is no problem, but once you go to network storage, that's a different story. And as you can see, security is not always only a local thing, because once you go to network storage and network connections, you also have to secure the other end. So, as I said, we're going to have a look at the resource use. We did do a couple of evaluations on some of these alternatives. For example, Docker containers, OSV, which is a unikernel platform, so micro virtual machines. A standard image on Firecracker, which is actually an alternative runtime for micro virtual machines. And Google gvisor, which is kind of a virtual runtime for Docker containers, which inserts itself between the container and the host kernel. So here we can see the actual performance in terms of a REST application. So you can see these are pretty okay. So Docker is in terms of its native. Docker is basically native performance. There's no actual limit on CPU performance in containers. So we can assume that this is native performance. OSV is actually faster than native performance. So you can get isolation alternatives that are faster than actually running the process on your host itself. Firecracker is a bit slower. Mostly has to do with drivers it uses and how it allows the internal process to access the system resources. gvisor is unexpectedly slow because, well, it's a software kernel basically, which makes not only a software kernel, but it runs in user space. So everything it does a lot slower, but it's secure, which is kind of a big trade-off to make for more security. In terms of memory, here we can see, yeah, we have a native process using almost no memory at all. Containers have a little memory overhead, but then we have all the virtual machines, which add a lot of overhead onto each and every process. So again, if you want more security, you're going to have to pay the price for it at some point. So you can possibly have better performance, but you will have some other resource that's impacted. Moving on to data security. So we already discussed devices, the actual software running on it. What about the data it generates? So you can have local violations, of course. You can have local intrusions, physical intrusion, or just leaky programs leaking data all over the place into files. You can have bugs in hardware that leak data all over the place. You can have networked leaks too. Of course, these can be intentional and unintentional. For example, you can have bugs in your program that leak data, whether you want it or not, unsecured connections to remote servers, or you can have someone simply connecting to your device and stealing all the data. Again, much more likely if your connections are unsecured and have no authorization whatsoever. There's no silver bullets to data security because there are many sub-aspects to it. But, well, what helps us secure software, encrypted connections, which is really the basics, decent authentication, authorization, and basically assuming that you are operating within a very volatile environment. You don't trust anything, you don't trust other processes, hardware even, just assume zero trust and build up from there. And basically, the only way to really not lose data is to not generate it or to not keep it around at least, which will come back when we talk about AI. Best way to ensure privacy is that once you have used the data, you just toss it away. You still have to make sure it doesn't leak anyway while you're processing it, but that's the least likely option. Talking about network security, actually. So again, this is a very hostile environment. You have to assume that a bunch of devices and people are going to try to connect you to your device, try to get data out of it, try to corrupt it, try to compromise it in every possible way. So first thing you have to consider is, what other actors can be nearby? How do we have to protect against this? This can be accidental. You can have an entire system of domotics in your house, for example, that operate on certain ports, certain services, and then you can have something else that interferes with it. This is accidental, but it can lead to network problems, data loss, all kinds of stuff, especially if one of the two systems is a little bit less reliable in terms of privacy. It can also be because of the user, of course. Users themselves can install bad or shady software. We see this in the news all the time, with people losing all the money in their banking accounts because they installed something weird or did a couple of weak actions. This can be related to social engineering too, of course, but you also have to take this into account. And then it could be, well, fully intentional. Someone can just deploy or try to deploy botnets on your network, and a couple of firms get in and compromise your devices, and before you know it, everything gets leaked to China. Again, well, basically assume zero trust. And at least for networking security, we do have AI intrusion detection, which is these days very successful at detecting malformed packets and actual attacks with malformed package. Coming into the more practical aspects, last time I introduced a project called Fuse that we worked on. Fuse is basically, well, just to say it once, the federated unified service environment, flexible federated unified service environment. Basically, this is about the federation of private networks into one big whole in case of emergency services. So we also want to give full control, full granularity over what gets federated. You don't just federate the entire network. You get to decide which parts you federate here and there, just specific resources, so you don't have to share your entire company network. An important aspect of this, of course, is speed, because you have to be able to join the cluster quickly enough in case of emergency situations. The performance has to be high enough because we're dealing with camera streams in possibly degraded situations. Reliability, of course, again, dealing with with degraded situations in terms of networking. The traffic still has to be able to get through. And a third factor is ease of use. Again, you have to be able to set it up with one command, just real quick, no doubts, no fiddling around in emergency situations, just go and it's running. So let's imagine, for example, that there's a huge monster on the loose running through the port of Antwerp, causing fires and a couple of explosions on its way. And all the surrounding companies need to federate their camera streams in order to see what's going on and respond to the situation. What is the actual architecture of Fuse, well, the way it was designed is with a Docker and Docker approach. First off, we have the crisis center and the actual companies. Each company actually gets federated into the network of the crisis center. So it's not that a bunch of separate companies are joining together the networks without control. There is an actual crisis center taking care of all the orchestration at a high level. So the crisis center has the master nodes. Basically, this contains a VPN server. This is only to actually consolidate all the separate networks into a coherent whole so that we can deploy services on it. The actual crisis center also has a VPN client for its own deployments, because inside this first Docker environment, we have the Docker and Docker container, which runs all the workloads. So this is basically only the networking aspects and isolates the entire network from the rest of the system. Well, this is an extra layer of isolation that runs all the workloads, for example, a monitoring dashboard. At the companies, we have the same thing. They join the network. This is basically the first layer of isolation from the rest of their corporate network, which simply allows them to join the Fuse network. This is one uniform address space, which makes it a lot easier to handle for the crisis center. And then you have a Docker and Docker environment, which runs all the workloads deployed to them, which are very specific to their devices, of course. But they are also only able to access only those devices, as we will see on the next slide. This way, you create a uniform network environment that allows services to run in a more or less equal way, without impacting the security of each individual company, and still allowing them to determine which resources to put into the federation. Looking more at a high level at the networking aspect. So here we have the VPN network. And you can see that there's a couple of resources being used by each company. For example, company A has some cameras, which we really want to use. Company B has some free storage that we would like to use for maybe looking at the camera streams later. So company A, despite being federated, still cannot directly reach the storage of company B, because that would be a security violation. No, it actually has to go through the pod network of company A. There, the camera streams get processed, and the crisis center can orchestrate it so that these camera streams are redirected to the worker nodes of company B, which are able to store it in company B's actual storage cluster. So despite everything being accessible, well, technically, you still have no security issues between companies or even between the crisis center and the companies, because the crisis center still can't access the cameras directly either. Looking a bit more into performance issues, or rather how performant it is. As you can see, if there is no network issues at all, so if the network is still basically intact, there can be some fires, explosions, anything you want, as long as the wireless or wired network is still intact. The start time or join time of Fuse is actually very low, like on the order of 10-20 seconds, which is suitable for an emergency situation. Of course, as network degradation goes up, the join time increases, which is kind of related to the Kubernetes version we were using. This was a bit of an older version. The newer versions have an actual heartbeat mechanism. They have leases, all stuff that reduces network traffic, which makes it, which makes the join operation a lot faster. Also, even in emergency situations, this is very extreme. You're unlikely to get a 400 milliseconds ping when you're only communicating over a couple of kilometers. And you're not going to get 20% packet loss either, because that's basically a total collapse of your network. Looking at application level performance, we tested this with HD video streams, or rather, not full HD, the half HD. And we see that, well, basically, when there's no network degradation, we can have about 10, maybe 20 streams active at the same time, without corruption, fully visible. which is decent enough to ascertain a certain specific situation. Of course, as degradation sets in, yeah, we start to get some really bad performance, which is basically due to the way how TCP streams get handled by the Docker and Docker encapsulation. So this is basically the networking problem, which can be solved by looking at the type of virtual network we're using. So to solve that problem, we had a bit of a look at all the different VPN alternatives. At first, we were using OpenVPN. Of course, OpenVPN is a bit older. It's very flexible, but since performance is critical, we do need to examine the other ones as well. So we also had a look at Soft Ether, Think, WireGuard, and Zero Tier. And basically, WireGuard came out on top, which isn't much of a surprise, since shortly after that it got mainlined into the Linux kernel. It's actually almost flat in terms of performance, so it doesn't matter how many clients you have. WireGuard gives you a static performance. So whether you have 50 clients or 500, same amount of throughput is available. There's also the same response time. We also looked at a bunch of other metrics, but basically WireGuard came out on top every time, sometimes by orders of magnitude. So that was the part of security. Now we're going to get a little more into orchestration itself on the IoT and in the edge. First, we'll have a look at virtualization runtimes. So we saw these guys a few slides back. Now, security is definitely not the only aspect of considering a specific runtime for your software. There's ease of use. For example, Docker is very popular. It's also very easy to use these days. Some of these other tools, well, of course, gvisor has the same tools, but there you have the performance issues. Some of these other tools are quite difficult to use at the moment and still under active development. Another aspect is, well, can you actually run existing software, or do you have to recompile it? How do you have to recompile it? Do you need to change your software? Do you need to simply recompile it using APIs of the runtime? Or do you need to use an entirely new language? For example, a subdialect of C that's only available for that specific runtime. Compatibility, for example, does it support certain software standards? Can it integrate well with, for example, existing orchestration like Kubernetes? Can it even use all the hardware we need to use? Does it have decent community support? Is it actually still alive under active development? How many developers are there? Is it just one guy maintaining this thing, or is there a really big community that can develop tools when needed? Resource impact, like we saw in the previous, or rather a couple of slides ago. The resource impact is quite big for the edge, especially for micro VMs. But there is an up-and-coming alternative, WebAssembly system interface, which is proving to be quite good in terms of performance and doesn't use a lot of memory either. One thing with WebAssembly, however, is that it's still under active development. There are some missing features, but it's definitely something to keep an eye on. And, well, also related to WebAssembly, does it actually support the entire Linux system interface? For a long time, this was a problem for OSV unikernels. They had, they didn't support all the actual system calls, so some of the network support was a bit patchy. We actually had some research into WebAssembly to support some of the network functionality of Linux too, which enabled us to, for example, run Kubernetes operators with WebAssembly. So if we have a look at the NVIDIA Jetson Nano, like which alternatives can we actually deploy on this device? So there was a lot of talk about all the different runtimes. For example, Docker has excellent support, but it's containers, so it's not the most secure option. Kata containers is a bit more secure, but it's quite resource intensive due to combining two alternatives. OSV, actually great performance, great security, but hardware support is a bit patchy. There's one device that it might work on completely, another ARM device it may not work on at all. For example, Raspberry Pi 4 is now supported, but there are other devices that are much more stable. gvisor, of course, wherever Docker works, gvisor will work, but it is slow. WebAssembly, as I said, is still under development, but great resource use and isolation. And then we have Firecracker, which is basically more of a platform than a runtime, but it also has some decent performance. But again, it was made for the cloud, not specifically for the edge. So when we look at what we can actually run on this device, practically, we get this. So basically, gvisor is also possible, but it's not very practical. It's too slow to really use on an ARM device. We did some benchmarks on that, and it only gives you about 5 to 10% of the performance of Docker, which is actually really bad. The problem with Kata containers is they use too much resources. The overhead is massive compared to the service you're trying to use. The same goes for OSP. Even if the service runs, you still have like 10% of your memory used by the overhead load. WebAssembly system interface is not quite ready, but this is something we are keeping an eye on. And Firecracker, well, the same problem as OSP. Most of your memory is used simply by the runtime itself. Now, if we're having a look at not just, for example, Raspberry Pi, but real microcontrollers, tiny embedded devices. So can we, for example, pull those into orchestration? Can we somehow get flexible service deployments on there, or flexible software deployments on there, and include them into the entire computing continuum? Of course not, right now. None of these alternatives can be run on microcontrollers because they simply don't have an operating system or any sort of kernel. But we are looking into that, and we are hoping that somehow we can make these devices useful for a flexible computing environment. Now, when we look at orchestration, so a level above the individual devices, we have, first of all, some non-Kubernetes, basically Kubernetes-based, non-Kubernetes-based. There's the alternative to Kubernetes from
Eclipse,
yeah, which is IOFog, which is basically already aimed at the fog and edge. It's deployable on, for example, Raspberry Pi devices. It's completely available. You can just go ahead and install this and use it. And it works pretty well. It also has a great community, good support. So this is a nice one. There's also the more commercial ones. Yeah, for example, Azure IoT Edge, which doesn't really allow you to set up your own edge cloud. It's rather more that you deploy agents on your devices, which are then managed by Azure in the edge. Still useful because you can push workloads to the edge. It's still very flexible, but you do need Azure, of course, whereas IOFog simply allows you to set up your own platform, much like Kubernetes, and manage your entire cluster yourself. And then there's the Google Edge solutions, which are basically the same as Azure IoT Edge. You get the cloud solution. You start setting up your edge devices through the cloud. You can deploy software, but all in all, IOFog is still pretty much the most flexible one. Of course, the commercial ones do have integration with their other products. You can store all your data, analyze it, use it with all the other products from Azure, from Google, from Amazon, possibly. But they can be quite resource intensive. All three of these can be quite resource intensive because, well, they are in complete platforms, essentially. So you basically deploy the entire orchestration and management software and runtimes on your edge devices. Except for Azure, which is quite efficient. But unlike the Kubernetes-based solutions, these are actually specifically developed for the edge. So in the future, this will remain edge-oriented and they will support edge devices explicitly. When we come to the Kubernetes-based solutions, there's a lot of alternatives there, but basically they all boil down to the same thing, Kubernetes itself. All the other alternatives are basically the same source code, but compiled a different way with certain plugins standardized, a couple of options taken out here and there. But because they're all based on the same code base, they all have the same resource use, which is very high. One major advantage, of course, is that they are all intercompatible. They are all highly standardized based on the container standards that Docker and Kubernetes contribute to. But their resource use, like I said, very high because they're designed for the cloud. Even the ones like K3s, KubeEdge, that has a bit of edge flavor in their description, they still have a very high resource use, on the order of sometimes 500, 600 megabytes per installation, which is basically impossible for an edge device right now. So looking at one of the projects that we did that was related to orchestration and edge computing, there was a short introduction about this last time. So the FlexNet project ran for 4 years, if I'm not mistaken. The basic setup was to enable multimodal networking and fail-safe computing. So on one hand, we had multimodal networking, so fail-over networking really. One option goes down, the others are still around. And on the other hand, we have edge computing that even if the entire network goes down, you still have your local processing capacity. And whenever network connectivity to the cloud is back up, you just synchronize with the cloud. So this was an international project. Our part was mostly involved with edge computing. And the primary use case was, again, guaranteed security, but this time in the workplace itself, not for accidents or emergency situations, just monitoring the workplace for dangerous situations and interacting when necessary. So a couple of results from this project. Basically, we developed the Fledge runtime, which is an alternative agent for Kubernetes. We'll talk about more about this in a while because it's grown very big by now. This is designed specifically for the edge, so we developed it specifically for the features we needed for FlexNet, tossing out all the rest of Kubernetes, and basically starting out from zero. It's written in Golang, so it's completely Kubernetes compatible, but anything that didn't need to be supported just got thrown out, which results in a very low CPU use and memory use. Of course, in the beginning, it still ran Docker containers. So basically, it was designed to run Docker containers on IoT gateways and on edge devices. And this was also validated in a demo setup. So basically, we demonstrated this entire setup with edge devices end user devices communicating with the edge device for local edge computing, multimodal networking to the internet and to the cloud. And whenever the internet connection fell, basically dropped out, we did continued with local processing. And there's a demonstration about it in 2 slides. First off, the actual architecture of Fledge. So in the cloud, we still have a Kubernetes master node as usual. But what we do on the nodes is a bit different. Kubernetes usually has the kubelet running on nodes. Instead, we have a Fledge agent, which offers the same basic API, but it's implemented very differently. First of all, we have the Fledge agent running over an OpenVPN network, again, similar to Fuse, because we needed to kind of federate the different, well, not really federate, but we needed to be able to access client devices behind, for example, network-added translation or firewalls. So you have a VPN network connecting all these devices, creating a uniform network environment. And on top of that, we have Fledge agents connecting to the actual Kubernetes master node, which in turn communicates with the container runtime to run all the devices, all the services that are orchestrated by the master node. The OpenVPN client itself is also run as a container, so basically the entire solution is self-contained. You can just set it up with a script, you can tear it down again, and everything is gone. But as you can see, the network connectivity involved is quite intense, which leads, or possibly leads to some performance issues when combining certain types of traffic.
How do you do an addressing inside of this network? So, for example, if the Kubernetes master node wants to deploy something on node 2, what does it use in order to communicate with node 2?
Do you mean on the level of the VPN or higher level on container level?
So, for example, what host name or IP address does it use in this specific example?
Yeah. So this is based entirely on IP addresses because we didn't include DNS at this point. So basically, the VPN network is something that creates the uniform network environment. Kubernetes has no real knowledge of this. What it works with is these. What it works with is these container networking addresses. So each node has its own address pool, which are mapped by Fledge, by the setup scripts, and by the Fledge agent to VPN addresses, which in turn are mapped to by the VPN network to physical addresses. So Kubernetes only really communicates over the container address network, and the rest automatically gets converted to VPN addresses, which in turn goes over the physical interfaces.
And then does Fledge also give this container network address to the Kubernetes master node so that it knows where the worker nodes are?
In this version, the Kubernetes master node completely decides which container addresses are assigned to which nodes. So once you connect a Fledge agent to the Kubernetes master node, the master node decides, or rather the CNI plugin decides which range is assigned to that node. The Fledge agent queries the master node for that range, and then it can set up the entire environment.
Let's say you want to have a similar kind of overlay network, but without Kubernetes. Is this possible, or is this specifically built for Kubernetes?
This is specifically built for Kubernetes, but we'll come back to the non-Kubernetes version later in the presentation, because that's something we're also working on. So a bit more into the components of Fledge itself. This is mostly based on the virtual kubelets technology developed first by Intel. Yeah, Intel. Which was really basic when we first started to use it. Now it's grown a lot more capable, and it can handle actually all of Kubernetes functionality. It's grown along with Kubernetes, so to say. But the virtual kubelet actually represents a fully Kubernetes compatible kubelet inside the Kubernetes API. But once you get to the device it's running on, it can represent anything. This is basically just a REST interface to the rest of Kubernetes, nothing more. It's just a fancy name for a REST interface. Behind that, we have the Fledge broker, which kind of decides which runtime a certain workload should be run on. In the beginning, we only really had Docker and Containerd as alternatives, but we're going to talk about REST in a couple of slides. This Fledge broker talks to the container runtime interface, which then takes care of all the rest of, for example, container networking, C groups and namespace management, resource monitoring. And what we use as a container runtime is basically just Containerd. In order to load and start container, image management is done by Fledge itself. And once the container is up and running, Fledge takes care of basically every aspect of container management and container running.